like faded.
I'll try to scream at it. Okay, guys. So number 3 on the complex section had us going from, this was the one that had inches and feet in it, and you may have had to look up the inch to centimeter conversion. So it started us off with 23.6 feet squared, and it said to get 2 centimeters squared. That was our question. So in this case, you first had to think about how to get from feet to centimeters, and that may not be something you know, but you might know how to get from inches to centimeters. So the very first thing I did was take 1 foot to inches. Okay, oops, not 1 inch, 12 inches. So, but what did you add to this, those of you who attempted this one? If I can get this conversion right, that'd be great. This is supposed to be 12 inches. What did you add to this? Did anybody do this one? Thank you. So did you go straight to centimeters? Okay, you could have looked it up, but I'm going to go with a standard one we might know. Okay, well, everybody should be able to tell me, if that foot is squared, what do I need to do over here? Square it and the number, right? So everything here needs to be squared. So this is squared inches, squared feet, squared number, squared number. Okay? And then that's going to allow for our feet squared to cancel. Now we have inches squared. We have to convert to centimeters squared, which is possible. Okay? 1 inch is equal to 2.54 centimeters. That might be something you maybe learned a while ago. So if I want to take inches to centimeters, so I'm going to put inches on bottom, centimeters on top. But the inches are squared, and so everything over here will be squared. But I'm going to go ahead and insert my conversion first. 1 inch is equal to 2.54 centimeters. So if I have to square the unit, I have to square the numbers as well. And that's, I like these because this is the one that you'll probably forget on the test, so I'm trying to get you kind of used to this. So the inches are squared, canceled, and so then we're to centimeters squared only in our unit, so then we multiply across 23.6 times 12 squared times 2.54 squared. Everything else on the bottom is 1. And that answer is a big number, 2.19 times 10 to the 4th centimeters squared. Thumbs up, you get this one? Okay, it's just that one funky little conversion you may not have been aware of. Number 4 on the complex had us going from 952 grams per liter. And so though it says slash liter, write it as a numerator and denominator explicitly. It makes your life a lot easier. And its question was to go to grams per millimeter cubed. So if we're going from, what do you notice is not changing first of all? Grams. So don't even touch the numerator. Leave it as is. Work from the denominator up and then keep going, okay? So you'll notice you're supposed to go from liters to millimeters cubed. There is no straight up conversion between liters and milliliters cubed, but there's a starting point. We have to start with liters. What's a good place to go from there? Milliliters, right? We can really easily go from liters to milliliters, and there's a reason. Because in the back of your mind, I'm going to write it down here, you know 1 milliliter is equal to 1 centimeter cubed. Do we remember this from our density? If you don't write it down someplace, I'm expecting you know this now. Okay, I'm expecting you can use this. And it's easy to get from liters to meters in that way. And then eventually we'll get to millimeters cubed in just a moment. So 1 liter contains 1,000 milliliters. I think is probably your next step here. And your liter here will cancel the liter here. So now I want to cancel out milliliters. What's my next step, everybody? I'm actually not going to touch grams because the grams themselves are staying constant. Go to what?
Milliliters?
I can't go from milliliters to millimeters.
Milliliters to grams. Yeah.
I can go from milliliters to centimeters cubed. Right? That's why I write this here, so you can put it right there. It's still a 1-to-1 ratio. It doesn't matter. The numbers are going to be ones, but it shows me that you know how to get from 1 milliliter to 1 centimeter cubed. And then eventually you'll take your centimeters cubed to millimeters. And that one's a metric system conversion. So King Henry died by drinking chocolate milk kind of comes to mind. So our milliliters here and here cancel. Now I need to get to millimeters cubed on the bottom. And I need to get to centimeters cubed on top because I need to see this cancellation occur. But what are the numbers that go here in accordance with the metric system? Right, who gets the 1? 1 centimeter is 1 away from milli, right? So it's got 10 millimeters in it. But what else do I do to this because of the nature of the units? I will cancel centimeters cubed after I first show myself cubing everything, because that's what we do with the cubes and the squared units. So centimeters cubed, cancel. The only thing left for us to actually numerically calculate then is 952 divided by 1,000. Here and here. Divided by 1,000. Because everything else is ones. So then that would be 9.52 times 10 to the -4 grams per millimeters. Because the only things I have not canceled yet are grams per millimeter cubed. And so that's grams per millimeter cubed. Whew. Okay. Yes, sir. On this section too? Okay. Number 2. This is the one with the meters. Is this right? Meters cubed to kilometers cubed? Oh, sorry. Kilometers cubed to meters cubed. Okay. So the first part of this was 1.467 kilometers cubed. And so if you're going from kilometers cubed, the question asks to go to meters cubed. Very first, ignore the cubes and just tell me how would you get from kilometers to meters. What has to go on the bottom? Kilometers. And what has to go on top? Meters cubed. And I'm just going to stick away from the cubes for just a moment. How do we convert between these? What are you visualizing, or is it on your paper, whichever way you wrote it? Okay, so you're using the number line from K being 1, because the 1 is the larger unit. 1 kilometer has how many meters, which is base? 1,000, like you said, 3 zeros away. So then now I'm going to show the kind of cubing part of this. Cube, 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 just cube the whole thing, okay? And then that's going to show that your kilometers cubed cancel here and here, leaving you with meters cubed, but the number needs, this is a billion, so 1.467 times 10 to the 9th meters cubed is what that would be in scientific notation with correct sequence. Okay? All right. Hold more questions for PS3B for a moment. Go ahead to turn to the word problems that we were doing last week. We were doing 10 through 14. I'm going to do 15 with you guys right now, okay? To show you that you have the power to do this with crazy, crazy problems. Oh, I just wrote all right there. So look at number 15, and then what are you familiar with in this problem? What words and units even?
Seconds.
Okay, seconds, right? Meters. What else? You maybe have heard of wavelengths before, like wavelengths of light, but a lot of the stuff might be kind of foreign. So like I'm telling you, I don't expect you to even understand the entire question. I expect you to know how to problem solve. What are the 3 things we look for when we are doing our problem solving? The given, the question, and conversion factor. So when we're looking at this, I want you to read through and you tell me what you think the given is. And circle it, put G underneath it, something. This is number 15 on your paper. So, Luke, what's the given here?
4,000.
That is a good starting point, but I'm going to read that a little bit differently. A photon of visible light has a wavelength of 4,000 angstroms. That A with a halo is just called an angstrom. Don't worry about it yet, but it's a unit of measure. So it's actually saying this wavelength has this. So it's actually setting up an equivalency. The symbol for wavelength is lambda. It's this weird looking kind of broom. Okay, it's saying that is equal to 4,000 angstroms. So I bet half of us thought that was a given. Keep reading. Which is the given? No, what do you think? 3 seconds. Notice it's a data point. It's not compared to anything. It's not paired with anything. There's no fractional unit. So we can dissect a problem, okay? So this is the given here. If that's written as an equivalency, that first one up top, that's called a conversion factor because they're comparing each other. They're saying they're equivalent. What else is actually looking through the whole question, how many conversion factors are given? 3, right? The first one we just circled. This one that's randomly here in parentheses, 1 angstrom is equal to 1 times 10 to the -10th meters, and 3.00 times 10 to the 8th meters per second. Those are 3 conversion factors. Probably going to have to use them all. We'll see. What is our question Vincent, what are we looking for?
How many wavelengths will pass?
Okay, stop there. So how many wavelengths, right?
Yeah.
Right there. So our question is wavelengths, number of wavelengths. All right, so now we don't need to look at the question, really. We just need to pull out those pieces that we need. So we identified all these because we know we have to start with what? What do we always start with? The given. And so we're going to have to start with 3 seconds, as is. And I write SEC, but it's just this. So if I'm just walking myself through this puzzle, how do I figure out which is the next conversion factor? Yeah.
Convert 3 seconds to the speed of light. Right?
So I'm going to use the speed of light as my next conversion factor. Because you look here, here, and here, there are no seconds anywhere except for the first conversion factor. So I have to use that. How do I write it? What goes on top?
3.0 times 10 to the 8.
Right, so this number stays with the meter. It has to stay on top. And this 1 second, which is as a slash here, is going to be on the denominator, 1 second. Okay, the only reason we did that is because nobody cares about seconds, and we want to cancel them. Okay, now we are in meters. So, Brock, tell me the next one that makes sense to use. So we just use this one here. Look at so the 3 conversion factors. You guys stay with me here. This is conversion factor 1 we've already used. This is another conversion factor, and this one up top is a conversion factor. We want to cancel meters, so which would be the next one to use. All right, Alvin.
The first one is number 6.
Right. Why? How do you know that? Right. So you're simply looking for the one with meters in it because it needs to be used to cancel out these meters because nobody cares about them. So this is going to go down here, but how do you want to write it? How do you want to write it? What goes on top, Alvin?
1 angstrom.
So 1 angstrom goes on top because that's a unit we want to get to, and this one's going to go on bottom because it's the unit that we're going to use to cancel this meter here and here. All right, so now we're in angstroms. SJ, last one. What's my next conversion? So we have used this one, top one. How do you write it? What goes on top? Okay, tell me what goes on bottom. The way it's written, it's not written as a fraction, so you have to write it as a fraction. Right, so the 4,000.0 actually angstroms, and the little lambda, that's 1 lambda or 1 wavelength that goes on top. So all we gotta do is calculate now. We take our angstroms and they cancel out, and so we're in the units that we want because that's what Vincent told us we wanted wavelengths. Okay, so calculate right now. I want to make sure you guys plug this in calculator right. You want a calculator, I would like for you to practice in however way you can. This is a calculator you want to use. That's probably wise or that's calculator. Here, pass that over here. Anybody else? Calculate. Take about 30 seconds and put this baby in your calculator. All right, what'd you guys get? Thank you. 2.25 times 10 to the
Times 10 to the 15.
times 10 to the 15th. That is the correct answer. You might have a lot of zeros if you need to count, need scientific notation all the way. This is almost the right answer. Wavelengths, okay? Almost. If you did not put that in your calculator right, I guarantee you it was probably in this little area here. You need to put parentheses down here because when you say divided by 1 times 10 to the negative 10th, your calculator is like, oh, we're putting that on the numerator. You need to put in parentheses and keep it in the denominator if that's what you're trying to do. I just don't want you guys to work so hard and have all the right work and have all the right answers on paper and not be able to calculate it, right? So just double check that for yourself. Help your partner if they need to, your neighbor. And then how many sig figs should this contain?
2.
Okay, so our natural inclination is just look across the board and go, oh, 1, because there's 1 everywhere. But remember, anything that's metric, we ignore. Like this is a metric conversion with angstroms. That was us defining it as 1 wavelength because we needed to compare it to 4,000 angstroms. And that's kind of not in the metric units, but it's a constant. So if you don't know which one it is, always start with the given. And the given sig figs, and this one is how many? 2 sig figs. This one should be recorded to 2 sig figs. So around that, 2.3 times 10 to the 15th wavelengths. Yeah.
I got instead of 13.
Probably you just missed a decimal. It's the 4,000 probably in the back. I'll look at it. Okay, guys. So go ahead and any more questions on PS3B? Yeah. Sorry. What else? What's your question now?
I was just wondering about the 14.
The word problem 14. So amount of heat given off when water condenses is that. So that's a conversion factor. Molecular weight is that. That's a conversion factor. How much heat, so question kilojoules, is given off when 15 grams of water condenses. That's our given. 15 grams of water. Good question, because on Friday when you guys take your test, I take up your portfolio check, which is everything I've asked for you to do. And that's a free 100 if you've done it. If not, then we got problems. So 18 grams per mole is our next step. 1 mole on top. So I've used this conversion factor here. Grams of water canceled. Moles of water is my next step. I need to get rid of it. And so that my second conversion factor is here. 254 kilojoules per 1 mole. And that allows for grams to cancel, moles to cancel, and me get to the unit that I was asked for, which was kilojoules or joules in this case. Kilojoules in this case. So that's something like 208 or something. Let's see. Anybody have the answer? 211. Okay. Okay. Anything else from PS3B before you guys turn that in? I'll get that inside for you. Yes, ma'am. 15 from 3B, the word problem one is the last section. How much water will be displaced, right? So this was worded probably weird more than anything, but it's not a difficult problem because in number 15 on the word problems, it gives you the mass in the problem of 200 grams, 200.0 grams. It's asking for the volume because when it says displaced, it means space that's being taken up, that's being displaced, and so it's kind of between the lines saying volume. The density is given in the table above for aluminum of 2.7 times, or 2.7 grams per centimeter cubed. So if you're looking for volume that's being displaced, then I would solve for volume using the density equation or using dimensional analysis. So 200 grams of aluminum. And if I take this density and I flip it, the grams are on bottom, which allows me to cancel grams. So 2.7 grams on bottom, 1 centimeter cubed on top. That's going to give me volume of 74.1 centimeters cubed. And that amount of volume of the aluminum, being when it's placed in water, it will exactly replace the same amount of water because they're taking up the same amount of space. So that's also the amount of water that would be displaced in that example there. Or if you write this as centimeters cubed, that's equally the same as saying 74.1 milliliters because those are interchangeable. Good question. That was a good word one. Yeah. 18. Yes, ma'am. Okay. So this will be the last one I do right now, just because I'm going to get into our physical and chemical changes for today. We have an activity we'll do kind of close to the beginning here. So this is another good one. You have one similar to this on your test, because I just finished up making those tests. 18 gives you a constant. It gives you in the word problem 3.20 moles per liter. That's one of the conversion factors it gives you. And then it tells you for barium chloride or BaCl2, it tells you you have 0.42 moles of it. So if this is all you see, and then the question that's asked of you is liters of solution or just liters, you guys tell me, where am I starting, where am I going, and how am I ending? That's all you need. You don't even need the word problem. Yeah. So there.
How I did it was I just did 3.2 moles over 1 liter,
Mm-hmm.
and then it equals 0.42 moles over 19.
So you solved it like a proportion. We're trying to, that's cool, but I want you to try to stray away from proportions to dimensional analysis. So give me the starting point. What's our given, guys? 0.42 moles. Okay, and then I've checked, I've used my given. What has to come next? Which is the conversion factor. So am I going to write this conversion factor? Am I going to write it as is here or flip it? I have to flip it because I have to put the 3.2 on bottom, which is exactly how you solved it because you probably divided, okay, in your problem, per 1 liter. And then that gets me to liters. Ta-da! We're done. So that one is a one-stepper. Probably like, what is that? Point, I have this answer. What am I doing? 0.13, thank you. I'm going with 2 sig figs, so 0.13 or 13 liters. Okay, so go ahead and pass out 3 B's for me. And then, oh, I had a couple people not turn in their density level with their groups. Oh, Max brought, I don't have yours. And then other people, Nana, I think you make Nana. Some density. And Morgan, I was wrong, because you were doing the notes from the other day. All right, so while you were passing up 3B, please pass back this little printed notes that I have for you guys today. Okay. There might be extra there. Okay. Yep, passing up 3B and passing back this little set of notes. So we'll just talk about matter for about 5-10 minutes, and then I'll let you get your activities together, and then we'll finish up with properties of matter, and then so if your partner or your buddy is absent, please make sure you're taking an extra sheet from them, for them. Alright, make sure you're taking good notes for your partner out there. Okay. Extras? Thanks. Alright, so this first part is basic review, I think, from like 6th grade, and then some from your reading guides 1 and 2, which I'll pass back. So matter, you know, we all have matter because we weigh something, so we have mass and we have volume, right? So this is basic definition of matter. That right there takes up space, has mass. So whenever we talk about matter, we are referencing pretty much everything in the universe. Our next unit, we're going to talk a lot about energy. That is the only thing that is not considered technically matter. So looking at these examples here, tell me which ones are matter and which ones are non-matter. So air. Raise your hand if you say matter. Thank you. Colin, tell me, why does that matter? Okay, because it's non-energy. That's an easy way. Give me a more direct reason why it is matter. Not because it's not something. What's in it? Thank you. Good. Oxygen. Carbon dioxide. What else? What's the 71% of the atmosphere? Nitrogen. So you can keep going, right? There's a little carbon monoxide, just to keep you on your toes there. Water vapor, methane, all kinds of gases are in air. Gases are matter because they are made up of elements. So you should be able to think abstractly about what's matter and what's not. Blood. Definitely, right? It's not just some vital force inside of you. There's plasma, there's platelets, there's iron, there's all kinds of things in there. Light waves. Why non-matter? Because it is energy, right? So can you see the light waves right now? You guys can't see the light waves? I see them. Okay? You can actually see the light waves because the light waves are interacting with your eyes, so they help you see. Not only do you see them, but they help you see. The reason they are around us is because that means the reason I know they're around us is because you can see color. And waves of light, hello. Hi. Okay, will do. Okay. Okay, gotcha. Thank you. Okay, you can see the light waves because they are creating color. And we know light waves exist because we know about photosynthesis, right? if you don't put, if the plant is in the darkness all the time, then it will never do its job. So it has to absorb energy from the sun to do so. So energy, chlorophyll only absorbs like blue and red, doesn't really like green. Why is that like very apparent? Because it is green, right? It reflects the green back off, and it doesn't allow it to absorb. Music. Why non-matter? What kind of energy?
Electricity.
It's not electricity. That would really hurt. Sound waves.
Oh.
Okay. So sound waves are a form of energy because they just do their job of making vibrations happen. So you're hearing me right now. Why?
Vibration.
But what are they doing to you? They're just hitting you in the face? Okay, going into your ear. Thank you. They're now good. So this is like an anatomy lesson, right? A little bit of hairs in your ear, and if the sounds are coming at you at a certain frequency, they wiggle the hairs in your ear. It's really deep in your cochlear membrane, okay? And that's not like the hairs in your ear. It's like inside. And they wiggle, and then they send that pattern of frequency wiggling to your brain, and your brain interprets it as a certain sound. But it's not this. That's just like a buzzing sound that your brain hears. It's not interpreting words until it's the language center of your brain, and it's interpreting like the vocabulary and the terms that we're using. Different languages, of course, you have different active parts of your brain, or just different knowledge, right? What's another fun fact I was going to say about this? Oh, how am I making these noises? So yeah, so what am I doing with my vocal cords? Well, how am I vibrating? Okay. That's breathing air, right? So you have to force your air to a specific part of your area here. I forget what it's called. It's not, it's a neck, but your tracheal area. And it's going to cause the different vocal cords. Some people's are thicker, some people's are thinner, and it's going to cause it to vibrate a certain way, and that certain way is going to come off and deliver a certain frequency. So we all can change our vocal cords a little bit. We can stretch them thin or make them fatter so you can get really high, get really, really low. So it depends on how you change the vocal cord. It's going to give off the different frequency. So that's our anatomy lesson for today. Okay, so water definitely is matter, right? Because it's made of two important elements of H and O, hydrogen and oxygen. Okay, so I gave you guys a flow map to help you organize your thoughts better, and you're going to be doing an activity related to this. I gave this to you so you can take extra notes so you can listen, but some of us are going to zone out. Try not to zone out. It's fourth period, I know. So where there are two big categories of matter, pure substances and mixtures. The pure substances are going to come in two varieties, elements and compounds. So the examples are really what I'm going to go over, okay? So if I say PTOE, what does that mean? Periodic table of elements. I have a couple up there. Copper, what are these other two? Iron and SN. Cans are made out of it. Not aluminum. Tin, thank you. Okay. What are some other elements you can find? There's a couple periodic tables in the room. Maybe you just know some.
There's like 3 in that folder.
Uh-huh. Do not say water. It is not an element. It's a compound. Hydrogen, right, hydrogen. Sodium. Neon. Helium. Okay, so anything that's a symbol. A symbol is going to be an element, okay? So it has to be a symbol from the periodic table. Those are the only things that are considered elements. If we start putting elements together, that's when we start actually making a chemical bond. And if it's chemically bound together, we call it a compound. So, chemically bound together. And if they're chemically combined together, they're quite difficult to pull back apart. So, each of these things, when they come together, they bring their own properties. So, sodium, for example, sodium is extremely flammable in water. Sodium metal, it sounds harmless. Drop in water, it's like an explosion. It's very, very flammable. Chlorine, so that's what sodium is, okay? Chlorine itself is like a very hazardous gas, okay? But we put them together, they make totally new properties, and that's something we can eat, right? Sodium chloride is table salt. So they have new properties as a compound. CMPD is compound. And that's something that's kind of more some background information about their definitions of compound. Another thing that makes them special is that they come in specific ratios. So if I give you water, that's the formula for water. H2O, right? So 2 portions of hydrogen, 1 portion of oxygen. If I change up the ratio, and instead I give you H2O2, you're going to die, first of all, and you'll know why. But why? It looks like water. Probably looks like water because it's clear. What is it? What's H2O2? Hydrogen peroxide, right? You cannot drink large amounts of hydrogen peroxide. It's quite poisonous. But it's the same elements. Why isn't it the same thing? Because what?
Different proportions.
Different proportions. The different proportions actually make it a totally new chemical compound. So that's why it's different. It's important to note that we do write these little subscripts down at some points in times. Okay, so I'm sticking with compounds for a moment. How do you, if I wanted to separate them, how would you do it? There's very, very few ways to take a compound back to its original form, meaning its 2 elements. You have to do it by chemical processes, and this part's not on your notes, okay? So if I'm going to take a compound back to its element form, or whatever it's made of, I have to do something drastic. I have to change its bonds. So that's why it says separation by chemical methods must break bonds. And one example of that is electrolysis. Who's ever heard of electrolysis? Great. Okay. We gotta get up. I just gotta get out more. Okay, how about lysis? How about the phrase or the suffix, lysis? Think back to biology. What does a lysosome do? It's ribosome. Helps with digestion. What's another word to say digestion? Go for it, Chloe. Right, so stop there. Breaking down. So the lysosome breaks down stuff. Guess what lysis means? Break down. Okay? So it's breaking stuff down via what? Electro sounds like electricity, right? So electricity is a method that we basically shock these elements or these compounds and they break back into their original form. Because we put forth so much energy to break their bonds, they do break apart. That's just one way, and there's not very many, so let's only have one example up here for you. Okay, good on chemical compounds. Write down what you need to. Electrolysis, breaking down compounds back to their elemental form. Electrolysis, breaking down compounds to its elemental form. Gosh, I printed notes for you guys. You could write down just a little bit more for me. Okay, I'll come back down to that in just a moment. All right, so these have defined proportions, like Carson was saying. They have defined proportions. Mixtures of it, on the other hand, sorry, let me scooch back up to mixtures. Mixtures don't have a defined composition. They're a blend of things. And so, let's say I'm making a fruit salad, and I like pineapple. I'm going to put a lot more pineapple in there than apples and oranges. So I'm choosing to do that because I'm making my own mixture. If you really, really like sweet tea and you like it to be very, very sweet, what do you put more of? Sugar, right? And so that's why it has a variable composition, because there is no defined composition for a mixture. It's up to you. And these are going to be physically combined together, meaning they don't have chemical bonds. So I put not chem, let me say no bonds. No chemical bonds between the different things in the mixture, maybe within the pure substances within the mixture, but not between things in the mixture. So that's going to make it different. It'll look different like when you look at a particulate view of these things as well. So they're always going to be pure. I mean, if matter is made of pure substances and you put stuff together, the mixture is also going to be made of pure substances. That's just kind of like how we don't have anything else to work with but pure substances. But you're going to have to look at them and notice that they're not going to be touching each other. They're not going to be, they're not going to be chemically touching each other, meaning no chemical bonds. So, 2 different phrases that we use to describe mixtures are ones that look the same throughout. Same throughout would be uniform. And my best example for that is salt water. How do you know something is salt water? It tastes like salt, right? If you look at it, what's it look like? Just water, right? You would never know it's a mixture until you did some more tests, some more trials. So salt water is a good example because you can't tell that it's salt water until you do something else. It looks the same throughout, but it's a mixture of pure substances. And so sodium chloride is our common name for salt. Is our chemical name for salt, and water is H2O, right? So is this mixture, is that a mixture of elements or a mixture of compounds? Right, and how do you know they're compounds? Right, because they're chemically combined, and they're chemically combined. Great. So you should be able to look at their formulas, their symbols, and diagrams of them to tell. Heterogeneous mixtures. So, we all know homo means same, right? Prefix homo means same. Hetero means different, okay? So they're going to be things like oil and water. So if I have a beaker of oil and water, who's on top? Oil, because it is, don't say lighter, less dense, right? We are now more informed. So there's a definite separation between the two phases, and so if it's very like defined, one part on one side, one part on the other, we say it looks different, and so we call it heterogeneous, or heterogeneous, or hetero, however you want to say it. Okay, so are mixtures chemically combined together? No. Any more no's? Great, zero no's, okay. So they're not chemically combined together, so I can separate them, right? All right, so let's say I have a solid liquid mixture. How do I separate them? Filtration, yay! So we remember from like before the snow. So filtration is a way to separate things off of based off phase differences. Solid liquid is a really common mixture that we will try to separate. What about distillation? What is that based off of? Say it again? No.
Separate like two waters, like two liquids.
So you do separate two liquids based off distillation, but how do we separate them? I heard it. Thank you. We're basing it off the boiling point differences, right? So I don't care when water and salt boil or water and paper towels boil. I'm just going to separate them with filtration. Doesn't matter what their boiling point is. Distillation works based off boiling point. And so I have to know their boiling points to do that appropriately so I can boil up all the water and stop boiling it before the next thing starts to boil off. So that's a little bit more a different physical property we're concerned with. Chromatography we'll talk about later, but that's another way to separate things. Okay? So look at these diagrams, and then you guys tell me. I'll come back to this other stuff later. Okay, looking at the diagram right here. Tell me, first of all, do you guys see pure substances or mixtures? Why? So looking at this one right here, why is this a mixture?
There's two elements.
Okay, so you see two different things mixed together, right? Inherently mixture. That blue guy, you see there are two dots right there, right? Is that, I know that's a pure substance because that's what mixtures are made of, but which of the pure substances is it? Say it again? On that side, yes, that is a compound. How do you know that is a compound?
Those are like
Because they're combined together, they're touching, they're chemically bound, and there's two elements that were used to make it, right? So I've got compound blue and compound green mixed together to make that looks homogeneous because it's very well distributed throughout, right? Looking down here at the black and yellow one. Mixture, compound. Mixture or pure substance? Okay, first off, big picture, it's a mixture because it's stuff mixed together that doesn't look the same. But what is it a mixture of? Every mixture is a pure substance. Which ones? Why elements?
They're not compounds.
Right, mixture of elements because they're not compounds because they're not chemically combined together. And this to me looks more hetero because it's like black area, yellow area, black area. So it's very different in terms of their phases or kind of the way they look. The hetero part is sometimes difficult to tell. What about this one over here? So obviously a mixture because you're like, I see different stuff going on. Mixture of what?
Compound and elements.
Right, blue compound and kind of a pinky element, right? So you can see it because there's singletons. So you now have like symbols and pictures to work with, okay? So we're gonna do an active hero class. Claim a partner. Look at them now. I know you need to look at them so you can claim them. And whenever everybody needs a piece of paper. Everybody needs a piece of paper. Let's see your starting. This is just a quick classification of matter activity. We took a long time on the warm-up.
Miss Emily, I need Emily Horn to come to the office for a minute, please.
Thank you.
Thank you.
So this classification of matter worksheet, it says A through infinity. because you're going to get a card set, and I'm not sure how many cards are used because sometimes they mix up. So all the cards, I need you to first classify them as pure or mixtures, and then further you're going to break them down into two categories of mixtures and categories of physical. It's working with a particular diagram, talking to a partner on it. Everybody's writing down what they need to, and then we'll turn this in. What are we done when I call time? Okay, so come back here, get this part out. It'll do that. Not really partner, but partner's really good to bounce ideas off. Work wherever you need to be productive.
Do I need a note?
Take the monkey right there. Yep. That's it says here. Short and sweet is our middle name, okay? So if you need to write 2 words to get the point across, I get it. If you need to write 2 sentences, I get it as well.
Description of the mixture. So we just make descriptions for all of them, basically.
Oh, for that first one? Yeah. This is right here. This is on your sheet, so take extra notes where I'm indicating and I'm saying a lot, so write down what you need to. But I'm sticking with physical for now, we'll come up in a second. Physical properties are very observable, right? Some of them, like color, size, shape, are things that are observable. Things that are not really observable, but you know, are things like melting point, boiling point, freezing point. So, I'm going to get this to move. These right here, boiling point, freezing point, and melting point. So if you don't know what the abbreviations are for, there you go. They're not observable, but we know they happen. Because I know that I can melt ice at what temperature? What is the melting point of ice? Or what's the freezing point of ice? 0 degrees Celsius, right? So once I cross that threshold, either way, either going above 0 or below 0, something's going to happen to the phase of ice. So I call that a physical property because I know something is an inherent characteristic about water. But the actual changing part, so actually changing from solid ice to liquid ice, that part, that change is called a physical change. And so that's the next slide. You can see it on your paper. So we use the physical and chemical properties to describe more about why the changes are actually happening and why they are occurring in the way that they're happening. So these other characteristics that are physical characteristics or physical properties, ductility and malleability. Ductile and malleable, you guys familiar with those? What are they referred to? So what's the flattening one? Malleable, right. So to be able to flatten and to like take a, metals don't look like, jewelry and maybe even ductwork or anything like that in your house. They don't look like that. They look like rocks. And so we pull the metals out of the rock. We extract the ores from the rocks. And then we take that big lump and we flatten it into like a flat sheet and we use it on machinery. So to flatten metals out is a term that malleable term. Ductility is a kind of similar to that, but it means to draw into a wire. And it's just to stretch out to a thin, long wire. That's all that means. And so ductility is going to be commonly referring to metals as well, because that's what we have wires made. Half of our wires are made of copper. How about conductive? What's something that you know is conductive? Metals, right? So you already know metals are conductive and non-metals are non-conductive. But these properties allow us to categorize it like we are, metals and non-metals. So all these properties are going to be used to classify matter into big categories, like what we've been saying, metals, non-metals. What's the one that's a mixture of, or has the properties of both, right? Metals and non-metals is a metalloid. So we can use these inherent properties and we can classify them into metals, non-metals, and metalloids, or even pure substances and mixtures if we need to. So that's what physical properties are referring to. Inherent characteristics kind of directly related to their composition. Before we do chemical, I'm actually going to go to physical properties and physical changes. Can I go forward? Yes? Okay. So the physical changes here, there are some really easy ones, and I'll tell you the ones that are less easy. Let me get my Play-Doh back here. If I have a big ball of Play-Doh, I know you're envying me. This is just going to be a spherical shape, right? And I can really easily smush into a non-spherical shape. Now it's an oval, right? Can I go back? Can I revert back to the way it was, right? Most of the physical changes are reversible, okay? And you can go back to where it was really easily. It's pretty low effort to do so. So if I'm going through phase changes, I'm going from solid to liquid to gas. Those can maybe be reverted. Right, I can melt solid to liquid. I can do what to liquid to make it gas? Say it again? Heat it, so boil it or evaporate it, kind of a different term. Evaporate, I can go that way. What happens, or what's the term used to go from gas to liquid? Condensation, and then going from liquid to solid. Freezing, right? Those are all phase changes, and those phase changes are changing of the phases, those physical states of matter, and that's why it's considered a physical change, not a chemical change. Yes, ma'am?
What was the process called from gas to solid?
So the one that goes, that's a good point. This is our one that most people forget. Going straight from solid to gas. Anybody? Was it S? Sublime, right? Sublimation or sublime is a process of going straight without any liquid occurring, okay, from solid to gas. Dry ice is a great example of that. You've seen dry ice, which makes a kind of smoky foam or gas. Or air fresheners. Do you ever see air fresheners go to liquid? Or do you just smell them? Think about it, you just smell them. You never see air freshener go to liquid phase. They go through sublimation and they get smelled in your house. Backwards from gas to solid is called deposition, and we see that quite frequently in the winter time when it frosts on the ground, because it goes from kind of gaseous water particles in the air, it goes straight to solid as frost. Okay, so if we're ever changing the way something is shaped, that's called sculpting. The most common example of changing form, though, for us, is dissolving things, and so a really great example of that would be salt water. Salt water is going to be just two compounds mixed together, but I take a big lump of salt and I put it in water. What do you see? What's it look like afterwards? Looks like water, maybe cloudy water, if anything, but water. Can I get the salt back out of water? I can't. How? I could distill it to get the salt out. That would be way too much energy.
Would you filter it to like?
But the salt's so tiny, it would go straight through the filter.
Yeah.
You could boil the water off. That would be a good way. I'm just going to say evaporate the water off, and that would leave behind the salt, so you get this nice crusty salt kind of thing on the bottom of your beaker, whatever you're evaporating it from. You could totally get the water off, no problem whatsoever. Whenever you take food coloring and you mix it with water, what happens to the water? Changes color, right? So if you take red food coloring and you add it to water, you're going to get red water. Did you expect that? Yeah, like, duh, everybody knows that. But what if I do, hold on, I don't have my goggles, safety glasses. Okay, turn around, my dears. I also don't know which way. Okay, so you don't know which pipette went with which one. You don't read the pipette, okay? Ooh, you don't contaminate this stuff. Okay, so clear liquid. Yes. Ooh, ah. All right. Okay, did you expect that? Yeah, totally. Clear liquid. Okay, another clear liquid. What's gonna happen? What color's gonna change?
Blue.
Are you just guessing? Did you expect that? Okay, so color change is on the fence, right? Color change can be expected color change. And is expected color change a physical or a chemical change? Physical, because it's just a mixture, like food coloring is just a mixture with water. You could take the food coloring out if you wanted to, but it would be really hard. This is actually something called a precipitate. Okay, have you heard of a precipitate? Okay, the color of the precipitate is what color? Yellow. The new substance that we form is yellow. It's not because a color change occurs, because we actually formed something totally new. That's why it's called a chemical change and not a physical change, because we formed a new chemical compound. This is lead to iodide, slightly carcinogenic, so that's why I'm getting that too. Okay. One year I had somebody who actually had cancer hold it in their hand, and she was like, "My tongue is on." I'm sorry. So, all right. Let's finish up our notes, and I'll do so. I have like 5 more demos for you back there. So this is my favorite part. So the physical changes, the kind of the theme that you're going to see is that they're all reversible. Some of them are easier than others to reverse, but they can be reversed, meaning they're not going to be a new chemical form. For the chemical properties, so the chemical properties are inherently related to chemical changes. They're more about the reactivity of the substance. Some of these words, where did you see these words before? Well, you're doing that? Okay, you may have seen actually some of those in your density lab. I'm thinking more the safety activity where you guys put chemicals together because of their chemical properties. Do-do-do. We finally have chemical properties now, okay? So the chemical properties are coming into play now because they're going to help us describe how they react and maybe the changes we're going to see with them. So flammability, what's an easy way to say flammable? Okay, fire. Okay, so we're going to see that it can catch on fire. Reactive just means that it's going to, that's a really big word that means lots of things, so we'll get into that later. Oxidizer means that there's an exchange of electrons. Exchange, so EX delta change of electrons, and so that's actually going to force the chemical reaction to occur because electrons are very reactive. Acidic we'll get to. Decomposes. What's a really good decomposer in biology? Worms are, what else? Bacteria, fungi. I'm going to stick with fungi for a second, okay? All of those are decomposers, but fungi is my favorite one. And what do they do to matter? They break it down, they decompose it. So do you think they form new things? Smaller things. They chemically break bonds, right? So fungi or any kind of decomposer, they chemically break bonds. Like, for example, cellulose, which is like a huge carbohydrate, right? Fungi or any kind of decomposer breaks it down into its elements, carbon, hydrogen, oxygen. So they actually are chemically changing the matter. So that's why most of these things are inherently related to their chemical changes that can occur. So, I don't think there's anything else here. No. Chemical properties, done. Chemical changes. There we go. All right, so this is when literally a chemical reaction occurs, like the one I just did. So we actually can write out the balanced chemical equation for it too. If I wanted you to write out the chemical equation, we definitely will later on, but I can have you write it out now because you can show the reactants forming products. Secondly, that new product that is formed has new properties. Because that very first, the demo I just did, we took clear liquid, we put it together, and what do we make? Yellow precipitate. And a precipitate is a solid. So I'm actually going to scooch down to precipitate first, and I'll come back. It is a solid. And I don't know if you can see it. Do you see the darker yellow on the bottom? If you hold up a different color, can you hold like a black piece of paper or something behind it? Or anything? Okay, well that works. You can kind of see it. Okay, calculator. Let's see what the calculator looks like. Yeah, I kind of see it too. I don't have my glasses on. So, the very bottom there's a layer of solid film. You guys can see it. The rest of us will see it later. All right, so the precipitate, the example or the definition of precipitate you might want to write down is 2 liquids together produce a solid. And in this example, the solid had a color. It was yellow. Not all solids will be yellow. They'll be white, they'll be pink, they'll be blue, they'll be all kinds of colors. So sometimes with it there may be a color change. Maybe. It depends, but we can generally see the color, yeah.
Does it change, like, the solid from compounds or change in temperature?
Change in compound. It changes the compound, and that new compound that's formed is not soluble in water. So if it's not soluble, it stays solid. Good point. Another thing that we've kind of mentioned already is the fact that we can make a chemical reaction with this. The best example I have for you is...
Attention students, if you ride bus 1170, please report to the bus parking lot at this time. Again, this is only for students who ride bus 1170. If you do, go to the bus parking lot and meet Ms. Walker at this time. Thank you.
Anybody? Peace.
Over.
Finish. If you gotta go, you gotta go. But I'll have about 5 more minutes of notes to just watch the rest. Okay. Okay. Homework is online. You'll see there's a link. Click the online link tonight. Okay. Bye, guys. Okay. So let me finish this up for you. I'll finish our demos. For example, the rust is the formation of iron plus oxygen. 2 different elements come together to make a new compound. These are 2 words that are kind of more advanced terms, right? Evolution of gas. What's a really fun way to say evolution of gas? Bubbles. Okay. Sorry, I was trying to get you to say bubbles. It's just making gas, right? Combustion means make fire and heat. Generally, that comes with combustion. So there are all these evidences of chemical changes that we are very aware of, but now we need to put terms to them. The theme on all of these is that most of the time, if I make bubbles, are they ever going to go back to what they came from?
They're like,
They're gone. They're out of here, right? Probably never. If I make fire and heat, it's very hard to capture that and make it go backwards to where it came from. So the reversibility is just not there for chemical changes. That's another key point to note. Okay, along with fire, heat, you also want to add the term light, because a lot of times it'll be very bright. And I hope that we can see that. Now, I put my glasses back on. Really back here? Okay. So that's it for notes. I'm going to have some pictures in the next slide. I'm going to show you this. So,
that's just
this
like
right here,
going on.
turn around. Let me show you about cities. This is a substance that is slightly, you can't see it, you have to stand up for this. Okay, so this is an indicator, and just a specific color and a specific pH. Okay, so when I put acid in this, it's going to change color. So right now it's green. Let's put some acid in here. Okay, so it changes color. And that color changes because the indicator that's in there is a huge molecule. It has characteristics that give it certain colors in different acids or bases. When I add base being a higher pH, it's going to change to a new color. What color do you think it's going to change to?
Oh, green.
Blue. Purple? What purple there? Okay, so what's going to happen if I add acid? It might go back to red unless I'm really careful and I have very little acid. If I go back to blue.
Would it go back to green first?
Oh yeah, it's definitely going to go through green. It's the rainbow. It goes through all the colors. Oh, that was fast. So that's a very transient color change, but it does get blue, yellow, or green, yellow, and then it goes to red. So that's an indicator. Indicators are chemical indicators, so they just determine something about the chemical properties of the matter. I'm going to show you a flammability. Actually, okay. So, yeah, let me use this table. So this looks like what? Cotton. Okay. Cotton. All right. So the cotton, what happens when you catch it on fire? Okay, it burns. Does it leave a residue? Yeah. So a little chemical change here. Okay, ready? Okay, so is that, do you see any residue here?
Yeah.
I mean, like, do you see burnt cotton? Lies. Lies. There's no cotton here. This is nitrocellulose. Who's ever heard of nitrocellulose? That was awesome.
Can you do it again?
I have another one. Hold on.
Wait, can I get it for the snap?
Oh my gosh. Sure. How about let me just hold this fire away from people. I have to stretch this thing out. So the way this works is that this is not just cotton. This is nitrocellulose, which is a chemical change form of cotton, which is cotton mixed with nitric acid and sulfuric acid that I've neutralized with some touching my hands. Don't worry, I'm not endangered. So I'm just going to stretch it out a little bit to give us some more surface area. A little oxygen up here. Okay. Watch your eyes, folks. You ready to be wow? Ready? Set? Nice. Okay, so that's nitrocellulose, which is inherently flammable because it's doubly catching the fire. I have one more example for you. I have 5 minutes left. Yes. Sorry, Sam. I'm leaving this right here. I need that. I don't want to waste my time. So, calcium. Where's my calcium? Calcium. What do you know about calcium?
It's in milk. Makes your bones strong.
It is in milk. It makes your bones strong. Is it flammable?
Yes, I think.
It is?
I don't know. We about to find
What
out.
do you say? Let me. Space here. Sorry, just back up. Back up what you're ready for me. You can get the calculator back up, yeah. Alright, hurry, because the show's about to start. Alright, I'm starting in 10 seconds. So calcium in water is hydrogen gas. Hydrogen gas is when, Sam, you're gonna hold that for me. You can hold the lip thing. Yeah. Just hold it. So, just hold that. So I'm putting some water in there and it's gonna evolve bubbles, also known as gas evolution, educated person, right? Okay. So you can see the gas evolution, you can really see it. I'll put a balloon on it. And we'll start to do that to the balloon.
Blow it up.
Blow it up, and then we're gonna blow it up. Okay? Okay. So, well, hydrogen gas, how do I prove to you it's hydrogen gas? Is hydrogen gas inherently flammable?
Yes.
Yes, thank you. Colin and Luke, you're gonna move to speak to the side. Okay, so I'm collecting all the gas. Ready, set. Whoa! There you go. So I'm not gonna catch the whole thing apart. Come on, guy. This is all hydrogen gas. So the hydrogen gas is still being produced like in excess. I should probably put this in the cube. Just don't breathe in the hydrogen gas, okay? You'll be fine. Really, you will. No hazards here. Okay, so I have another fun. That's really hot. Quite hot. So it's putting out heat, which is another form of chemical evidence of chemical changes. This fraction has like 5 different chemical changes. See if I can get it out of here. Okay, so balloon off. It's still making bubbles, but you know, I'm gonna die of early death anyway from all the chemical exposure. So this is phenolphthalein. It changes color in base. This made a really, really strong base, which I have in my hand a little bit. I'll be fine. Don't ignore me, guys. Okay. Phenolphthalein turns what color in strong base? Magenta. Very, very pink, right? And I'm not sure if you can see the bottom. Do you see that on the bottom? It's making a solid as well. So it formed a precipitate gas, color change, heat, and the hydrogen gas made fire. Calcium metal and water. Calcium metal, people. You eat this stuff. Okay, ta-da! That's all for you today. I'll figure it out myself. Excuse me. Alright, let me show you what homework is online really fast. Peace out. Never mind, you can check it yourself. Right there. On the top. Right there. It says click here.
Oh, fucking.